Yeah, you guys can be friends with Ian today. Fine.
But this isn't. This is the last day of class. Why are we doing this in the last day?
Because I wanted to totally throw you off.
His presentation is completely affected now.
Yeah.
No, that's the walk. Couple extra steps.
You're welcome.
He's so like, what's the words? Rattled.
Yeah.
You're so
That
rattled.
was my goal.
Makes me.
Because I'm pretty sure, just kidding, I used to go after you. I think you maybe spit that in the order.
You know, that is a good way for a speech class. Like, try to rattle people and see what would happen to them. Like, teach them that, you know, not everything can be perfect.
That's what we did for our honors class this semester. For the freshmen. Because they're supposed to create an argument that they shouldn't be at college right now. Which, I mean, is pretty hard for them to do because they obviously have reasons why they want to be at college right now.
Yeah.
And
Just have like parliamentary results.
yeah, pretty much.
I wish, yeah.
But then like us as as mentors just like totally just like threw questions at them like that I couldn't answer. So just trying to like we don't care what you say, we just want you to answer questions.
Yeah. Or with the question you go before me.
Huh?
I really want to get out of here.
Landon goes, then me, and I think it's you.
Yeah, you go before me. No, that's not good.
I don't know, your presentation could be better. Oh, and I know it could be. It's electron transfer. Oh, number 5. Landing goes first, but I guess it's his impression is looks at one thing and mine goes off.
Like, I'm just smiling thinking about it. Thanks.
It'd be good to
Figured
more.
out a little more snazzy.
Oh, yeah.
Give some eye candy
The-
for
So mine looks at different. It's hard to explain.
I have.
It was just completely based off of bond length, while mine also is bond length and shell.
But I'll see what you're kind of doing.
Okay.
5
Yeah.
minutes.
Sure. I don't even need this.
Do we miss anyone?
Might have been
Only one?
decent.
Like 6 seconds.
One.
Oh, really?
No, we miss Andrew.
Well, okay, you probably will.
Andrew Olson is not
Really
here.
just takes forever. It's just like watching one of those translators.
So we miss just 2, right?
Looks like it.
Okay, so before we start, I suggest we do a little of social activity. you remember the booklets from previous years. So for good memories, they do have photos of participants. So if you don't mind, I suggest we all line up here and maybe just this video camera would be sufficient. But if someone wants to take a cell photo, it is also fine. So it will go to the final release of the stuff.
Alright, friends.
Yes. And I have forgotten to remind you.
I was thinking of like an actual suit, but I was like, eh.
You need to word.
Yeah, no kidding.
I met my mom.
My friends.
I would
I call being attacked.
And all visitors are also invited. To,
Oh,
You can lay down on the floor.
yeah.
Just go like all the way up.
There's not too many of us this year.
That's fine. Well, since it is a moving picture, I can just move the camera from the left to the right.
Are we not there front?
Even out.
So that's
Why don't we do two
a
rows?
picture right now.
Well, the only problem, like the guys now on the left, they all have yellow faces. With some words on their faces, maybe you can
They're the
turn the presentation off.
It is.
Is it possible to
Is
get
it
out of the
possible to
presentation?
video mute and then unmute?
Yeah.
Can you do it for a second?
And you guys are here.
I don't know. If it is not easy, it's more important than.
North Dakotans. What are you expecting?
No.
Scandinavian.
I want to make all projectors dark.
the camera?
No,
Okay,
make
I can do it.
projections dark for 30 seconds.
Yeah.
Oh, I can hide you.
There we go.
There. Okay.
Are we just
So smile a couple of times, and you can go from the left to the right for better focus and maybe. If it will not be sufficient resolution at once.
That's my
Come in there.
You ruined the picture.
Sorry.
Picture.
What, should I be grabbing this or something?
Whatever you like.
Nice.
Can I do bunny
Oh,
ears?
okay. Now let's cover it, the whole.
You've done crazy.
Okay. It's hard to tell.
And where is London?
keep going.
Oh. Okay. So I suggest we all go back to the seats and start the actual
So
presentation.
was the photo taken?
Yes.
Yeah.
Sort of, kind of.
Kind of.
Angela, can you turn projectors
The
on back?
live action.
Quite panoramic.
Oh, I don't know if this is this.
Oh, okay.
That's good as up.
Yeah.
Oh, wait, I just dropped my
You're
stuff.
welcome.
Okay.
Beth is trying to rattle everyone on their very last presentation.
Figures after you try to rattle her on her last presentation.
Yeah. That's right. Hey, watch out.
Watch out.
Have some nice questions.
Do you?
As you probably realize, our main goal for today is to fit the schedule, so that those of you who need to go to other classes do not suffer. So this is the last meeting in the in work. In physical chemistry 364.
I remember it, but I just actually never remember.
So here's the list of subjects in class, and if we do not go into much details, some of you may go into teaching, some of you may go into industry, some of you may go into academia. And academic experience is a positive thing for everyone. And the activities in academia consist of three things. So theoretical background, practical skills, and scientific communications. So today we will test all three, especially the last one. Scientific communication. So you have made the research projects with selecting the subject, written the reports upon completion of the project, and now it will be very brief presentation. So how do we arrange the schedule? Please try, if you look into the schedule, you see that there is a 6 minutes assignment per person, per presenter. So they are split approximately this way. 3 minutes for presentation. If you go over, I'll become nervous and try to kick you from the stage. 2-3 minutes for questions, and 0 to 1 minute to walk in, there and back. Sometimes questions may take longer. The presentations are one of two main components towards productivity in the class. So if you convert it into points, 300 points for presentations and 100 points for answering questions, if any. The presentations are arranged in 3 groups. Well, sorry to the first 3, their faces are blocked, but they are there. You can see it on the printout. So, first group, approximately up to there, up to number 5, deal with deformance of electronic degrees of freedom in different chemical systems. Then about 3-4 presentations go into mixed performance processes in chemical systems when both electronic and nuclear degrees of freedom are important. And the presentations at the last but not least section of the screen dealing with chemical reactions where primarily interatomic distances are changing and their quantum properties may affect the outcome of chemical reaction. So, oh no, there is a little protocol. So, all of your presentations are uploaded to this computer. They are numbered according to the way you go, and the names include first and last name of the presenter. So what you do if you see Windows PC for the first time, you navigate to your number name, click, see its opening, and you click on this little symbol for starting the presentation. And after you finish, you may close it by little diagonal cross on the upper right. Just in case, you will most likely know it. So with this, I would like to... the little pieces of paper have program on one side and feedback on the other. So if you are part of the class, feel free to do feedback optionally. If you are guests, feedback is your main interest. And then I will collect it. So with this, I would like to invite to the stage Mark Emily, who will tell about electron and electric field.
So my presentation is an electron in an electric field with electrochemistry with arbitrary molecules.
You can use the, yes.
Okay, so so these are some important variables that I used. X var is the width of the electron wave packet, the mass. These are all in atomic units. The mass is just 1. The initial position is just where I started it. And, so wave packet, this is basically a copy and paste from an earlier presentation I gave, just to make sure y'all know about how the MATLAB program models the electron. The square root of dx essentially defines the one-dimensional space this is taking place in. And then the next part is the plane wave, how it actually propagates. And then the next part is the Gaussian. It defines the shape of the electron. And then the final part is normalization, making sure that the area under the electron is equal to 1. And then so other important parts I included how I actually modeled the electric field and atoms, molecules I mean. It just said zeros for one part, and then this part has this part of the space has a value of 1, this part of the space has a value of 0, and so on. These are very generalized. And then then what I did is I increased the slope of the electric field each time. So this first run I did was no electrical field, and oh, they're not running.
Describe the words. You don't have time to fix.
The electric field just basically, it just expanded into the electron, and some of it, into the molecule, and then some of it happened to pass over onto the right side of the screen into the second molecule. And then so this one actually has a YouTube link, so if you really want to see it, you can go check that out. And that basically did the same thing. However, some of it moved to the right more and more, and then so as I increased the slope, it got faster and faster. However, the movies aren't working, which was the main point of these slides. And then this one, basically, it all ended up moving over towards the right, and actually, maybe in the last one as well, it overcame the second molecule and just continued on moving into space. However, the simulation it stopped at the edge because the MATLAB system would have it come back on the other side if it weren't for my electrical field acting as a sort of barrier from that. And so, in summary, increasing the electric field increases the rate at which the electron propagates, and if the electron field is too powerful, it'll escape and go to the side. This was just sort of a general example of how an electric field affects an electron can be applied to a variety of situations.
Okay, let's thank Mark. And just in case you may test your videos by clicking on it, try it. If it not work, we are limited in time, we should go forward. Questions?
Well, I was just going to add on to it. Sometimes it's easier to exit out of the presentation and then start the video.
You may try it if you do not go over 3 minutes. Okay, questions to Mark? You did, please.
So in electric field, you talked about the strength, which was implemented through the slope, right?
Yes.
So means you're moving towards the towards the right. It's increasing the electric field, but electric field has a direction, right?
Yes.
Like
so,
you have in hold this direction being which way?
Which way electrons move?
Electrons move against the field.
If I recall correctly, electric fields push positively charged in their direction.
Mm-hmm.
So this would represent an electric field moving the opposite direction of the way that the electron moved.
So right or left, like according to your figure?
The electric
You can go
field
to
would have
your
been going to the
slides.
left.
To the left.
Well,
So the electrons move towards us, towards the increased field, right?
yeah.
If you will show the movies, and we will see how your wave packet is going to the right from the against the field and end up in the right side of the of your screen, right?
Yeah. And well, it would also work with positrons as well, theoretically, because in the code, the direction wasn't specified. So if the electric field's facing one, an opposite electric field would move.
Okay, so it means it was not involved in the code, right? So
Yes.
you're just assuming that because they move, like you just inserted the direction, and this direction was kind of either against, or you can say along the field if you change in the charge, if it would be not electron but a positively charged particle.
Yeah.
Okay. Let's thank Mark for presenting and answering questions. And now next presenter is Megan Schneider, who will continue the subject of electric field in more chemical reality in application to electrochemistry.
Okay, so I did the electric field as applied to anthraquinone. I chose anthraquinone as it has many other applications, including photosynthesis and redox reactions. Meaning because it's a carbon-based molecule, I can use a carbon-based electrode, and the wave packet should be able to transfer over it. So I modeled the electric field to see the strength of the electric field needed to make the transfer. And if this works, this is a video of what I actually saw. Goes on for a while, so I'm gonna let it stop there. The two methods I used were two different methods to calculate the Hamiltonian. And then these are the results I was able to obtain. And this was at an electric field strength of 0.01 AU, which you cannot see because it's behind the video. But the data 1 and data 2, so the blue line and the red line represent the two different methods. And the yellow line is a linear slope to determine the rate that was obtained. P1 being the rate, and in this case 5 times 10 to the negative 4th, with approximately a 20% transfer. And increasing it to 0.03 AU, the rate increases and so does the transfer. Increasing it to 0.06, the rate decreased a little bit, but the transfer still increased. And at 0.09, the rate is its slowest, but the probability of transfer is at 80%. So in conclusion, at an electric field strength of 0.03 AU, the rate is the fastest with a transfer at roughly 50%. And at 0.06, the rate is slightly slower with a transfer of roughly 75%. So depending on what you're doing and how long you want to wait for it to fully transfer, the higher strength of electric field gets you a higher transfer, but you're going to be waiting longer.
Okay, let's thank Megan. So any questions? Yes, please.
So similar to what Mark just presented, did you test at all if you just did like an obscene number and would like an electron kick off at all or anything like that? Or what would happen if your variable change was too high?
I didn't test higher than above 0.09. That's kind of where I cut it off once the rate started to decrease again.
Okay.
So you mentioned two methods for calculating your Hamiltonian. What exactly is the principal differences between these methods, physically?
The differences between them are the two different equations put into the code, but when they both come out, they come out.
No. What's the difference in these equations? Why is that different? What exactly? Which terms are different? What makes them different?
I don't actually know off the top of my head.
Well, you're using two methods and you don't know what's the difference between two methods?
Can you show equation when you present the methods?
What?
Can you show the equation?
Yeah.
So what is different? Which method do you show with this equation, and what would be different if you use another one?
So the top equation is our standard Hamiltonian, and the bottom equation involves the continuation.
So you define here your momentum or momentum squared. Mm-hmm. Is it always defined this way, or you have different ways to define momentum operator?
There are different definitions in the code of a momentum operator.
So they're different in the way how you define the momentum operator, right? And in one case you apply, so one is like matrix approach, so you have a kind of discrete set of momentum, and the other way it's more like a differential way.
Both are discrete, but different number of nearest neighbors are taken into account. So I was helping.
Thank you.
There is 1 minute more for questions. I have one. So in Mark's presentation, the larger the slope, the stronger the voltage between electrodes. And in your movie, the slope is changing. How do you interpret it, or what are you trying to model?
The slope changes in the video due to cyclic voltammetry rather than Mark's standard linear voltammetry. Cyclic voltammetry involves overcoming the potential. So as the system overcomes the potential, it decides to return in reverse back to the normal values.
Okay. Let's thank Megan. And the next presentation is by Jan Burke, who will tell a story about interface of two semiconductors and the impact of the interface of two semiconductors onto modern technology.
It's a lot harder to press buttons when you're looking over your hands up here. Okay, so I get to talk about semiconductors and their uses in transistors. So transistors, they're in your phones, they're in pretty much every electronic device ever. And they're basically brought to life by the use of these semiconductors. So basically what a semiconductor is, it's two different, or it's an element that has some movable electrons in it, but not completely like metal. And a transistor involves a p-n junction. It's kind of like the heart and soul of the on and off switch for the transistor. So there's a p-type and there's an n-type, and they're generally made out of silicon. And you can basically you can dope these with different doping atoms. Like the n-type, you would dope it with phosphorus because it's about the same and it has an extra electron. And p-type, you dope it with like boron, so it actually takes an electron out, so it creates a hole. So this is basically what, or that's what makes like the light switch, the transistors. So this image is basically telling us how a transistor kind of works. So basically on the boundary between the two different semiconductors, your n doped, so your negatively doped semiconductor has an excess of electrons in it, and your positively doped has a lack of electrons in it. So it's got a bunch of holes. So at this barrier, there's a certain distance where these electrons are going to disperse over and fill the holes in the positively doped semiconductor. So in this area right here, this is called the depletion zone. So this is actually depleted of movable electrons and movable holes. So when these electrons move over here, it actually creates a negative boundary on this part and a positive boundary on this part. So it creates an electric field. And then so this would be like a graph of the voltage and the electric field and what the charge has to encounter when you're trying to pass a current through it. So this is an image I pulled off of YouTube, but it's basically just illustrating the positive side and the negative side of the interface. So the next slide right here, this is basically talking about the strength of the depletion zone on the interface. So it basically relies on two different things. It relies on the voltage applied to the outside of the transistor, so that what the voltage does is it decreases the size of this depletion zone by this equation, or the potential difference of the current itself. So basically it's like the kinetic energy of how much current you're pushing through it to basically push your electrons past this negative barrier through the transistor. Right? So yeah, so basically the one that I tested was just increasing the kinetic energy, increasing the momentum of your electrons going through your barrier, as opposed to the voltage decreasing the depletion zone. So basically kind of what it has to get over is this is like your n-type, and what that image is showing is kind of like confined within the n-type as long as you have a lesser amount of kinetic energy. So, whoops.
Mouse.
I'm not pressing
Mouse.
any buttons. There we go. So basically what this one is showing is that I have my kinetic energy, I have my momentum set at negative 0.5 right now. So it's not very energetic pushing through the transistor, so it stops right at this barrier, right here. So it's confined to your one type of semiconductor. And then this one, I bumped it up to negative 1.5. So the energy level is actually above the potential difference of your field at the interface. So this one just flows right through it. It's got an open current moving through the transistor. So.
Okay, well, thank you. I see a question.
You said a semiconductor is a material in which the electrons are free to move, but it's not a metal. What's the difference between a metal and a semiconductor?
Well, a metal, the electrons within a metal are moving freely within the network, within the substance, right? But a semiconductor has the opportunity to move electrons throughout it, but it's not extremely free like a metal. It's
you need to put in energy.
Yes. Yeah. And then like this one, we doped it with like phosphorus, which introduced extra electrons. So then it has a limited ability to conduct electricity with those extra electrons in it.
Almost right.
In terms of energy band diagrams, it's a very simple explanation of what is it.
Of Venn diagrams?
Band.
Yes.
Okay, so time is up for Jan. Let's thank him for standing the questions. And the next presentation is by London Johnson, who will continue and probably finish the story of pure electronic degrees of freedom, and he will also tell about interface, about two different materials, but from slightly different aspects.
So I did my project on simulating the effect of interfacial bonding on electron-hole recombination rates in lead halide perovskite-based solar cells. So the basics of how a solar cell work is you shine your light down on it, and the normally it's just an n-doped silicon wafer and a p-doped silicon wafer. So the p-doped one, when the light strikes an electron, it'll excite the electron up into the conduction band through this band gap. That's what makes it a semiconductor, I guess, is that there's a small gap here. So once the electron is promoted to the conduction band, it's no longer bound to any particular atom, so then it can move around freely. And at that point, it can move into the N-type silicon and push current through whatever circuit you connect to your solar cell. If an electron and a hole meet, though, then they're going to recombine, and you're not going to end up getting any current out of there, so that is something that needs to be considered when you're designing solar cells. This is basically a schematic of the solar cells that I was trying to produce. I did finally get one of them to work out this way. I guess this isn't really terribly important to what I'm talking about right now. Okay, so these are both the through space model, and these are the through bond model. And basically the differences between the perovskite and the dye, they're either connected through space or they're connected through a methoxy linker group. That's what this little well is right here. And of course that figure is blocked. So basically that would just correspond to there actually being a connection right here on this diagram.
Can you explain what are those things that are connected or not connected?
This is lead halide perovskite. Actually, this might be a picture of a cesium perovskite. It's a perovskite either way. And this is the spiral dye. So then at low momentum, when you start with the electron over here and try to send it across the barrier, you'll see that most of it ends up reflecting back. You really get what's going on. Okay, there we go. So nothing really crosses this boundary. And now I'm gonna run these ones, I guess.
The one on the far left is off. Yeah. Not that one. No, one more to the left off.
Well,
Go all the way to the. One more left. Yeah, that one. Okay.
Oh. Okay, so if we start the electron with a higher moment. Okay, so if you start it with a higher momentum, you can see the wave packet actually transfers through this boundary. But an unfortunate side effect of the periodic boundary conditions that this simulation was running on is that you do have a significant amount of transfers happening across these boundaries, which is an unphysical artifact, and that needs to be accounted for when interpreting the data. So these are graphs that describe the probability of finding the electron either in the dye or in the perovskite. So the solid blue curve here is the one that we're interested in. This tells you the probability of finding the electron in the perovskite. So basically, after all of this stuff here, you're getting a lot of transfer happening through the periodic boundary conditions. So you don't necessarily want to be considering this data back here. So what we're looking at is just the initial, the early times when this is the only major transfer happening right there. So you zoom into these graphs, you just look at this section here and this section here, and you figure out the slope of this linear region to figure out the rate at which the electron is transferring into the perovskite. And you end up getting these transfer rates which have unphysical temperatures, but you end up getting a very interesting phenomenon where in the Arrhenius plot, it certainly doesn't obey the Arrhenius equation, because if it did, then the Arrhenius plot would appear to be linear. Instead, it appears that the transfer rate is just linear with, it's directly proportional to the temperature of the system. And that is
Okay, let's thank Vladimir. Questions?
Yeah.
Oh, so wait, okay. Professor Parton was the first.
Nietzsche, what was that? So you mentioned that when, go back to the slide 2, 3, where you're talking about the solar cell band gap thing?
Yes.
This one, yeah. You mentioned that when light gets absorbed by the p-type semiconductor, the electron travels through the band gap.
Yes.
Can you explain what you mean by that?
Okay, so the light has energy in the form of photons, where their energy is described by just the Planck's constant times their frequency.
Mm-hmm.
So if they have a high enough frequency or a low enough wavelength, then when they collide with an electron, they're going to impart that energy onto the electron. So as long as it's enough energy to actually get through this gap, because this is I guess the y-axis in this figure would represent energy. So as long as the photon has more energy than this gap, it can actually promote the electron from the valence band to the conduction band.
Okay, so
And probably you wanted to put arrow up, not down.
Yeah, I was in a hurry and made that squiggle the wrong way. But
if it doesn't have enough energy, does it get stuck in the band gap? Is that what you're saying? It's moving through the band gap and it can't quite make it all the way?
Electrons actually can't occupy any states within this energy. I forget, I guess, all the minutiae on how that works, but basically the electron would stay in the valence band and
No current.
Right, yeah, you wouldn't get any current out of that for sure. I want to say that the light would be scattered, but I'm not entirely confident in that. I would have to think about that some more.
Okay, so it doesn't move through the band gap per se.
And we have 3 minutes for questions. Just so you can complete your question anyway.
How are those barriers calculated?
These ones?
No, yeah.
These are files that were provided to me by Aaron Forty. He's done more thorough research in the same thing.
So,
So just parameters or like the various heights?
what are green lines?
Yeah, I suppose I should.
And how they correlate with the pictures on the top?
The green lines represent the potential energy. So if you look at it, there's basically, the electrons are going to want to be attracted to these atomic structures, I guess. So these are basically where the atoms are sitting in the perovskite in one dimension at least. And these are the dye here. And then this is just a little potential well, I guess, for the methoxy linker group between the perovskite and the dye. And then these lines up here are just the probability distribution of the electron.
So last question, where transfer is quicker, through bond or through space?
Through bond.
Okay, let's thank London once again. And the next presentation is by Christian Nunes, who will continue description of the same chemical system, but from the very drastically different point of view.
Thank you for the intro, Dimitri. So as you were saying, I am now studying the same type of reaction, but through Marcus theory. To start off, Marcus theory was first conceived of by Rudolf Marcus in 1958, and it was used for to look at the electron transfer of inorganic, organic metallics, and organic molecules. Here's just a general description of what a Marcus theory graph would look like. We have two different potentials, which both would correlate to a molecule. One would be an acceptor and one would be a donor. And what we're looking at is this intersection by these dotted points that it will be like the activation barrier in like the graph, the common graph we'll see, except this is just the energy we're trying to overcome the transfer of this electron from the acceptor to the donor. This gap, the HAB or 2HAB, is it's called I'm trying to remember the word. But what it means is the smaller this gap is, the less likely that the electron would be stick to the lower potential. But the wider the gap this becomes, the easier it is for the lower potential electron to jump back to the higher potential. So the substrates, as we discussed before, are a lead halide perovskite and an organic dye of tribenzylamine. We had two different types of the dye. We had the unfunctionalized one, which was just the tribenzylamine, and then the functionalized one with the methanol group. So these are just the substrates we're using. And then the very bottom here, we're showing what the type of scenarios we're going through of a through space interaction and a bond interaction between the methanol group to the perovskite. As you see that the perovskite is donating to, will be donating a proton to the dye while the electrons go into the perovskite.
Not proton, hole.
Hole. Okay. So the parameters for this, we're looking at mainly at the bond lengths, or I shouldn't call it bond length, but the distance between the perovskite and the dye. And for the chemical bond, it would be 0.64 angstroms, while the through space length is 0.24 angstroms. And as for the experiment, I started at a momentum of 50 just to see where to start. But I jumped up to 90 because that is where where I decided that the best optimal electron transfer starts, and I incrementally increased by 10 to 130. So here's the chemical bond scenario. I simplified the Marcus theory due to its more of a learning experience. So I set both the energy potentials to 0, so there is no offset. And I also made both the curvatures the same for each one. So this is not the true scenario between the two. The only thing that's mainly true to it is the length between the dye and the perovskite. So as we are looking at the initial momentum of 100, which is on the optimal yield I saw of the electron transfer. This moving part is the electron. And as you can see, every time it passes its intersection point, there's enough energy to transfer over some of the electrons into the acceptor. And as over time, you will see this will increase. Then we also moved on to the through space. There's a smaller gap between the dye and the perovskite. So there would be a lower activation due to the intersection point will be lower down on the energy potential. So as you can see, we start having a faster churn of electron transfer. So to determine the yield, we did transmission probability, and here's the graph of that. That's just taking the integration from the intersection point to the left and right. The left would be the product, and the right would be the reactant. And I decided to take the yield right around the 3 point. And as you can see over time, we have an increase in yield, meaning electron transfer was being achieved over time. Here's just a larger rate of scenarios. In this, you will also see the rate of the reaction. And from what I see, this is the chemical bond, and this is the through space. And you see that the rate of the reaction at 50 does not achieve, but in the through space, the momentum of 50 is enough to start transferring the electron over. It's with also a higher rate, but it decreases as you increase the rate. So we also are looking at how the electron shell shifts, because every time you move the electron over, it would shift over time. At the momentum of 50, you'll see because there's no electron transfer, the shell never shifts. While when I increase it to 130, over time, due to more electrons moving over, you will start seeing a shift over time. And here's just a plots of the rate versus kinetic energy. And as you increase, we'll see a quick increase in reaction rate through the through space, which is circles, and these triangles are the chemical bond. And you can see a faster rate increase, and the chemical bond is just faster overall through the whole scenario. So in conclusion, the chemical bond has a faster reaction rates than the through space, but the through space has a quicker reaction rate increase. Higher reaction yields yield further electron shifts, and there's a point in which the yields start to decrease because the momentum overpowers and the electrons are able to jump back and forth between the donor and the acceptor. We're looking at a very simplified version of this scenario due to just a learning experiment.
Okay, let's thank Christian. Although we are a little over the time, but are there any active questions? Okay.
Just for clarification, if you go 2 slides before, where you're showing this kind of step-like functions, previous. I mean,
oh, sorry,
before.
I heard you.
And another one.
Huh?
We're back.
One more.
Oh, sorry. That.
Just go ahead.
Another. Keep going further.
I should have.
Just keep going.
And another.
There you
Here.
go. That's
Okay.
Yeah. So could you clarify again? You said something about product and reactant, but what is a product in your case? What is a reactant? Product when coal is
yes.
transferred, or could you explain it?
So the product in this case is not a new material being formed. The product is the electron being captured in the acceptor. So these are the electrons starting in the electron donor, and over time, as more of these electrons starting in the donor goes to the acceptor, this will decrease, while these will increase over time because we're looking at electrons being transferred in the acceptor.
Okay. And the step-like shape of this function is due to just because you are taking your.
It's due to the electron. So as you saw in the video, so this electron moves to the right first, and so there won't be any transfer because it's not crossing this intersection point.
Mm-hmm.
So as it comes back, because it's being reflected off the barrier.
It's kind of reflecting the size of your well.
Yes, these are barriers, so it will be reflected off that barrier back towards the intersection point. We had it moving to the right first, so that's why you see these parallel.
Okay, and if there is no time for questions, write down your questions in the space provided. So quickly.
Why, I may have missed this, why is the through space lower barrier than the through bond in this system?
The barrier isn't lower. It's so due to the curvatures, and we have a smaller gap. These curvatures end up having meeting at a lower point than that's the chemical bond. So as you see here.
Yeah, I was asking why. Why is it like?
It's fine to answer. I don't know. It's,
Yeah,
because they are further away and they interact better.
Okay.
Okay, let's thank Christian once again. So next presenter is Austin Brewer, and he will continue presentations based on the same approach, same methodology, but he will apply it to different type of chemical system.
All right, yeah, I'm Austin. I have a good background in water. We're all chemists. Apparently, that's important to us. So, I'm pretty theatrical in this. But I really focused on the effects of initial momentum in the system that Christian was dealing with. And Christian looked at a lot of that through space as well as the bonds, and I specifically focused mainly on the bonds. I'm looking at a manganese semiconductor for quantum dots on that level. So I'll walk through quickly what we found out. So just quick background on quantum dots and why this is actually interesting research. Quantum dots are essentially semiconductors that are used to initiate different transitions in the phase of what's actually being emitted by something that is emitting light. So this has really big implications in nanotechnology, different kind of photovoltaics as we've seen in solar cells and everything like that. But that's just a quick background on them. And Christian also had a great background on what Marcus theory actually is. The only things I wanted to point out was the actual equation set up by Marcus. And what that includes is a lot of different variables. But the variable that I'm interested in most is really that energy barrier, that energy gap, and what's going to create the ideal situation for any kind of semiconductor, in this case, our manganese one. So the hypothesis of my research and what I focus my research on is, again, finding that optimal kind of initial momentum where we're going to see as much electron transfer as we possibly can. And I'll get into the details of that once we actually come to the data with that as well. So just to first of all see what these look like here. I can play both at the same time. It'd be awesome. So two optimal ones that I like to show for comparison is starting at an initial momentum of 35 atomic units and then also 100 atomic units. As you can see, the 35 atomic units is having trouble actually crossing this barrier and actually transferring electrons over to this manganese acceptor. Now, the one at 100 atomic units is having no problem actually crossing this barrier. So electrons are being transferred between this manganese and bromine bond that's in this complex that was on the previous page. And sorry, I can explain that later if you have any questions on it. What this means really is that as we kind of see this trend continue on, and as we see with some data here, I'll come back to that slide actually, but with the computational data, as we increase momentum, we're seeing a trend with all of these different outcomes. So the first outcome of kinetic energy is obviously we're seeing more kinetic energy in this bond system, and with that we're seeing more electron transfer. So as you can see, and I'll conclude too, that the optimal range here we're seeing is about between 65 and 100 initial momentum, where we're getting the most of our electron transfer in that semiconductor system. What we're seeing too is as we increase the initial momentum too, we're seeing a higher rate of reaction, or those electron transfers actually occurring. So this is just some visualized data. It's again with that the same time period, or I'm sorry, the same initial momentums as before. We're seeing in the first one, there's no electron transfer that's really occurring. There is some, but it's just back and forth. And then this last one down here, there's this back and forth that's continuously occurring, and we see the optimal kind of points that it's getting to. The rest kind of is what Christian already talked about. We're seeing not as much shift in the reaction coordinate or electron transfer, and yeah, those kind of go along with the trends that I already talked about. So in conclusion, what the research kind of showed is that there was kind of an ideal initial momentum between 65 and 100 atomic units. There's definitely a non-ideal initial momentum, which is interesting as well, ones that obviously don't make electron transfer shifts. And just focusing on what the future of the research can bring, looking at changes out of space with this example, or even through things like temperature change and everything like that would be something to pursue in the future.
Okay, let's thank Austin. Quick questions? Not quick questions, please.
So physically, how you interpret these different momentums? Like what exactly is the physical origin of for these parameters?
Yeah, so if I'm answering this correctly, what I understand as the physical changes that are actually happening is that as I increase the momentum of the system, there's more electron transfers from the bromine in this kind of octahedral environment, switching over to the manganese, which just creates what I would interpret as a more stable quantum dot. But I guess that could be up for interpretation, if that answers your question.
Well, it's kind of it's not exactly the question which I asked, but thank you. I mean, this is also an interesting point which you mentioned. No, my question is just in general, like when you say it has to be an optimal kinetic energy, right, for this or that electron. But is it coming due to the heating, through the through temperature, or what exactly making this optimal momentum?
Yeah, for sure. From my understanding of it, it would be the heating, and when we see in photovoltaics, for example, as we've seen, is that sunlight or energy from wavelengths and everything like that is what's creating that initial momentum.
Okay.
So
does it deal with because you have a metal center, right, and you also have organic molecules in a quantum dot. So can this momentum be also associated with a difference which you might change if you can change some ligands, or if you change in the metal center from one material to another? You probably expect that this also might change the kind of binding energy of your electron and maybe changing the momentum as well.
Yeah, absolutely. And I think if
chemical composition of material.
Oh, absolutely. If you focused on a different, quantum dot, for example, Christian's the perfect example. We did very similar coding, very similar processes, but he has a very different molecule or some kind of semiconductor that's getting far different results than what I'm getting. If you saw his kind of rate of reaction, it's very kind of stepwise, where mine, if you saw, was just kind of this continuous curve. So yeah, absolutely, chemical composition changes what's actually occurring in the quantum dot.
How many lead atoms are replaced by manganese? All or one?
One.
Okay, let's thank Austin. So, the next presenter is Aaron Polensky. So he will continue the same approach for a different chemical reaction.
Yeah. So my research kind of approached the same kind of concept, except where I was looking at.
Let me complete the introduction. When in this list of possible research projects, this project was labeled by initials Dr. AP because the idea came from Dr. Alex Parent. And Aaron Polensky recognized it as it is a prompt to use his initials, which are also AP. Good.
Yeah. So it was this was a reaction between a metal hydroxide and a carbon chain to form, not a metal hydroxide, a carbonyl and a carbon chain to form a hydroxide and a charged carbon. And so it was just to analyze to see due to the charged carbon being formed and with the hydroxide is not entirely stable. And so to get as much of that produced as you can, I was analyzing the transfer of the hydrogen from the chain to form the hydroxide. And so that's what we did here. So this is the coding that I used right away. So for my, where is it? All right, so for the mass, it is going to be that of just the single hydrogen that we were looking at because that's the only thing that's being transferred and moved around from the carbon chain to the metal. And then I changed, the P naught is what I changed at different points of the time. So I started at, I think I've had a 0.1 and I went all the way up to like 10 or something. And that's just the different energy levels that was used. And then there's something else. Oh yeah, the width of them is the wavelengths converted into atomic units. One is for the hydroxyl group and the other one is for the carbon chain. And then I think that's all I was going to talk about this. Next I have the actual data that was collected. Oh, you can't see it all, but that's okay. What's really important is the temperatures, I guess you could say. So I started with the 0.1 and I went all the way to 20 actually. 10 and 20 are at the bottom there. And so with the raw data, the slope is the production of the actual products. And as the temperature, or as the energy was continually increased, the slope did continually increase. What I found though is that this really did not, even though yes it did yield more, some of the temperatures really aren't actually plausible. So I came to the conclusion that temperature like at 81 Kelvin, probably the most like realistic temperature that would actually make the reaction go at an increased rate. I mean, anything else, you could tone it in a little more and actually find a reasonable value for your energy level. But I mean, I don't think any of us are going to get to 32,000 Kelvin anytime soon. So, and then I have some videos of the P naught at 1, or the energy at 1, I should say. And so you can just see that as the reaction continues, it will slowly, continually try to create the products, but then also at the same time, if you would like keep the energy level consistent, which it is, and you would run it for a longer period of time, it'll hit an equilibrium, and it'll just go back and forth and create and destroy the products and just keep going all the way. And then, here's the P naught of 10. This one you actually saw a lot more product actually formed because of the higher energy level. I think you can start to see it getting into the equilibrium at the end though, but I really just ignored that and only just focused on the beginning part of the data because no time can you ever have a consistent energy of anything like that. So that is the graphs for those. Oh, is there any question?
Okay, let's thank Aaron. And any questions? So can you remind what is the reaction? You didn't show
Yes.
the...
Yes, so I was going to draw it, but I'm not good at drawing. So it's of a...
Show by fingers.
So it's going to be of a metal carbonyl group, so a double bond and oxygen reacting with the carbon chain and taking a hydrogen from that carbon chain to produce a hydroxide. But then at the same time, a charged carbon is also going to be formed. And so it's really a reaction intermediate, and it would like react into something else. And so I was only focusing on the hydroxyl group. And so I only focused on that actual hydrogen transfer because I wanted to get that production rate as high as possible.
Okay. 1, 2, 3. Let's thank Aaron once again. You wanted to ask?
Yeah, I guess.
Okay,
Sorry,
quickly.
Aaron. So could you go back to like your first plot?
Slowly start preparing.
This one?
Yeah, or no, just the
Oh, this
first
one?
Yeah. Okay,
Oh.
so and then going back to the one you were just on. In comparison, those two graphs where you're seeing this kind of like position versus time.
Yep.
In the last one, it seems like there's a lot of static in between. You know, the actual.
This one?
No, the last one actually.
Oh, the last one.
Yeah, if you see, there's a lot of just kind of, you know, I can't tell
Yeah.
what's going on right in the middle. So what is that? What could you explain?
Right in the middle, that was just like interference, I want to say, because like it's not an ideal reaction, and so especially at this high of an energy level.
And what might interference like include?
Like the production of like other things besides the actual hydrogen transfer and stuff. So like at certain energy levels, it's just at a very higher energy level, and so there's a lot more momentum of the actual graph going back and forth, and so it like interferes with itself, kind of. So like cross the barrier, and then it'll go back through, and so it'll push more to the other side, and so it creates kind of, it just interferes with itself.
Makes sense to me. So it is neither coherent state nor eigenstate. Therefore, it is a mess. Okay, let's thank Aaron for the third time. So next presentation is by Braden Wake, who starts new chapter. From now on, we will be talking about more intuitive aspects. So there will be only one potential energy surface, but it doesn't make it less challenging. So there will be only one potential energy surface curve for different situations. And Brilliant will start with merging electric field and potential energy surface.
Alright, so I guess I'm pretty interested in modeling something similar to like infrared
It's hard to hear
spectroscopy.
you. Can you speak louder a little bit?
So I was interested in modeling something similar to infrared spectroscopy. So, infrared spectroscopy works off the normal modes of the molecule. So in the most simplistic settings, say you have like an H2 molecule that vibrates on one axis. So it's very easy to model this in one dimension. So we all know the harmonic oscillator potential, which I generalized to be offset from 0. In reality, of course, you can have dissociation of molecules, so it's not truly the harmonic potential, it's an anharmonic potential, but I've shown that on the right, but I've ignored it and worked with simply the harmonic potential. So to model the electric field, we've done the linear dipole approximation, and so that's shown on the top line there, where it's proportional to charge, the offset, and it oscillates in time, so I've attached a cosine function to it with some driving frequency. And I've reduced the amplitude of that, the Q and the factor, to just A for simplicity. And of course, the electric field is proportional to the displacement, so we can rewrite the displacement in terms of raising and lowering operators, just to kind of tie back to class a little bit. So what is the overall Hamiltonian? Okay, it's just an addition of the kinetic energy, the harmonic oscillator, and the electric field. Okay, so what I did is I took different situations of driving frequencies. So I set the intrinsic harmonic oscillator potential to a frequency of 1. Again, this is a very generalized system as well. So what I've done is I've taken the driving frequency fraction with the intrinsic frequency. So you can see 0.3 is 3/10 of the intrinsic frequency. And so I've run that, and as you can see, there's a nice peak when the driving frequency is equal to the intrinsic frequency, and we call that resonance, which is exactly how infrared spectroscopy works. And as you get closer and closer to the resonant frequency, you gain a better transfer of energy from the electric field to the wave packet. That's kind of how you can interpret that. Or a more efficient absorption. So visualize that. So here we have an electric field frequency of non-intrinsic frequency of the harmonic oscillator. And so you can see the energy absorption based upon the height of the wave packet on the plot with respect to the bottom of the well is roughly constant. And so the absorption of energy from the electric field is minimal. And so now we run the same simulation at the resonant frequency. So the scaling is kind of weird, but you can kind of see by the broadening of the potential that the wave packet is traveling upward. Okay, so a good way to analyze this, or the most simple way I should say, is to take a look at the, if you run it for a long time, you have sort of a maximal energy absorption, so it's like a saturated wave packet, then it kind of falls back down and restarts again, so it does this in waves, as you kind of saw in the very first plot. So if you take the maximal energy and you plot it against the driving frequency, or the frequency ratio in this case, you get this plot. And this coincides very nicely with classical resonance theory, which simply dictates that when these two are the same, you have a max. And that's pretty much
Okay, but then brilliant. Diane?
On the previous slide with the results, there is this extra broadening of the experimental curve that it's not there, right? Like this.
Well, yeah, when I plotted the theoretical curve, I didn't do any calculations for the broadening of the peak. I just wanted to show that the peak will line up with classical treatment. So the broadening term is here in this beta, which is related to the driving.
But the point in the middle that is right on top of the theoretical, and then as you go down, there's this extra. It doesn't look Gaussian. It doesn't look.
Oh well.
It
So
looks very weird.
all these points are very close together, so that's probably just some numerical error.
Can I help?
Sure. Yes.
Short pulse,
Mm-hmm.
duration of short pulse gives uncertainty in energy.
Mm-hmm.
And he is running simulation for a short period of time that contributes additional broadening. It should be convincing to you. More quick, yes. Please.
So if you ran it for a significant amount more time, it would be closer to the theoretical peak? Is that what you're saying? It would be less broadened if you ran it for longer?
Mm-hmm. More questions? Yes, please.
So you ignored your, you were showing in the beginning two potentials, right? One is harmonic, another one is anharmonic. And you were saying, no, I will focus just on the harmonic one. So could you give a physical reason or just tell when unharmonicity in a system is not so important and why you can neglect unharmonicity? And is it really applicable for your case, for your simulation? I mean, for real simulations which are shown on this black curve with experiment.
Well, the main result that would occur if I would have done the anharmonic is that the frequencies would be, of course, anharmonic or non-resonant, so it may not, so like overtones may not occur at integer numbers as well. That's a nice result of anharmonic. So the energy spacings between the states are not
Equally spaced.
equal to.
But you didn't answer why we can ignore this effect. Why we still be considering the system harmonically.
Because the attraction between I'm just assuming that the attraction between the two, in this case H molecules, is non-dissociative, and so it's like in the limit of small oscillations.
So close to its ground state, in other words,
Yes.
right?
Okay, let's thank Brian. And the next presenter is Andrew Olson, who continues the single potential energy surface description, but he will try to bring it closer to real world. So he will present on this practical reaction.
Alright, so I'll talk about the combustion of rocket fuel, specifically hydrazine and dinitrogen tetroxide. So there's three main categories of rocket fuel. Essentially what you need to know from this slide is that these two require an initial energy to overcome the activation energy, and hypergolic, which I am focusing on, it does not require. This says reacts on contact. So yeah, hypergolic fuel, it's spontaneous, like I just said. It's useful for really precise movement. So let's say you have a spaceship you want to land on the International Space Station. Because it's so instant almost, the movement, it's really precise and you can land it and get those really precise movements of thrust. But the downfall is that it is toxic, so they only use it at the moment for unmanned spacecrafts. So there's three main types of hypergolic fuel. There's hydrazine, and then these two, monomethylhydrazine and unsymmetric dimethylhydrazine. The only difference is in place of an NH bond, they add a methyl group. So when you add the two methyl groups, or the one or two methyl groups, the difference is that it lowers the freezing point, which is beneficial because they wouldn't need as much heating supply if they bring it in, if they store it in space. And then it also, the downfall is that it lowers the specific impulse or the thrust. So this is a representation of the activation energies. So as you can see, the blue is the N, and the white is the H. So the So the NH breaks as it overcomes that first barrier. Then you can see it slowly shifts over to the OH. So this is this green is activation energy, and this one is with 0 initial momentum, and as you can see, it still overcomes the activation energy pretty easily. Like I said earlier, spontaneous. And then for this one, just to get a different perspective, I bumped the initial momentum up quite a bit, and again, it overcomes the activation energy pretty easily. And this is the amount that goes to completion of the reaction. So as you can see, it jumps up pretty quickly, but it does get a little wavy, and I think that's due to just MATLAB error, because it did bounce back off the sidewalls on the video that you just saw. So yeah.
Okay, let's thank Andrew. Questions?
Can you go the slides where you're showing comparing two wells? This one. I didn't get, what exactly is the difference between your right and left?
This has a higher initial momentum, and this has a 0 initial momentum.
So it just changes the initial momentum of your of the wave packet, but the potential is exactly the same in both cases? Like your green curve is your activation energy, right?
Yeah.
So this activation energy is exactly the same?
Yep.
So it's affecting your overall potential in the same way. Okay.
Exactly.
More questions? Austin?
Yeah.
Could you go to that last probability slide?
This one?
Yeah, I guess I'm a little confused. You said that through this you determined that it like goes to completion.
Yeah.
Correct. Okay, so then what is, it looks like it crosses over twice and potentially is like leading up to a third time. So like what does that represent in the actual reaction?
Well, okay. Well, you see this slide, like as it goes across, like bounces back, and then it creates that wave that goes over this area again. So my idea that I got from this was that this like squiggly lines is just representation. It just represents MATLAB error. It's just kind of like, it doesn't look quite as clean on that side.
Okay, I guess if it's all right, I was asking more so, is this like an equilibrium almost, or it's going back and forth?
I don't believe so.
Okay.
Let me help. As soon as wave packet reaches the boundaries of the simulation box, results become untrustable.
Okay.
More questions to Andrew? If not, thank you once again. And the next presentation is by Hannah Fanut, who will continue our journey into the world of real molecules and chemical reactions, and she will tell about the catalytic reduction of hydrogen.
Yeah, like Dimitri said, I'm going to talk about the catalytic reduction of a proton into hydrogen gas for fuel purposes. Before I talk about my reaction, I just want to talk about hydrogen as a fuel source and some of its advantages and disadvantages. The reaction I've shown is the combustion of hydrogen gas with oxygen gas. And us chemists can clearly see the difference between most combustion reactions we think of, and that's that carbon dioxide is not produced. And that leads me to my first advantage, is that hydrogen fuel source is a clean source of fuel because it doesn't produce carbon dioxide like most fuel sources we traditionally use. We have an abundance of hydrogen in our universe. It is the most abundant element in our universe. Hydrogen gas is a much more efficient source of fuel than what we traditionally use, and it's much quieter than traditional combustion engines. There are some disadvantages to using hydrogen as a fuel, that it is highly flammable and has a tendency to ignite at very low temperatures. And it has very low viscosity, which basically means that it can leak very easily in a container through small cracks. And with the low viscosity, that also means it can fill up a room very quickly. So those two disadvantages can be a very bad combination. So strict safety procedures need to be followed when working with hydrogen. And I talked about there being an abundance of hydrogen, but hydrogen gas is very rarely found in the air because it's lighter than the air, so it's up above in our atmosphere. So instead of trying to obtain this hydrogen gas somehow, we can create it, and that leads me to my experiment. So I focused on the reduction of a proton into molecular hydrogen using a platinum catalyst, and this is the reaction right here. that I used. What is formed, the intermediate of the platinum catalyst, is this platinum cluster here. And actually, like you can see it right here, and it's centered with one platinum, and then platinums all along the sides, and hydrogens bonded on the outside. And heat is used to cleave the hydrogens from this platinum cluster. And I think it was about 2000 Kelvin it needed to be. And you can see here, like the hydrogens are starting to get closer together, and then after time, they start to dissociate from the platinum catalyst. And this catalyst is a heterogeneous catalyst, just meaning that it's in a different state than the molecule that it's catalyzing. And so my first challenge was just modeling this in MATLAB, the activation energy, and I did this based off data provided to me by Dr. Hahn. He had only provided me with 17 points of data, so I actually interpolated it into 97 points. And this here you can see is the activation energy for the breaking of the platinum hydrogen bond. And I used the wave packet code in MATLAB for this, and one of the major changes I made was it was set up for that of an electron and the mass was just 1, and so I changed it to about 1837 because the mass of a proton is about that much more than that times the mass of an electron. And then I ran this code at various momentums. I had a hard time getting it to look nice with positive momentum values, so the videos I'm going to show are all with negative momentum values. So this first video just kind of shows the reaction not proceeding, nothing's really happening because the momentum's too low or not low enough because I'm using negative values. And then that was about -6, the one where it didn't really go. And then this is about a -12. And it kind of just starts to go over and then goes back and kind of does some weird stuff. But then the lower or higher, more negative I made it, this just started to be higher in general, almost above it, so then it's definitely gonna go. And then you can see it just definitely goes over now because the momentum is much higher. And yeah, that is all I have.
Okay, good. Thank Hannah. Floor is open for discussion.
So in your slide with your simulations, you have again green, yellowish kind of, and red. So for the red, what is the difference between red and yellowish? Because they look pretty much the same, with the difference only that one is a little bit offset.
Yeah, so I know the green is the activation energy, and I'm pretty sure this yellow is just the energy of the proton trying to go over the activation energy, and the red, if I'm correct, is probability of the position of
The same as what it is the same story as the question that was asked to the speaker number 2.
Different method for your Hamiltonian, right?
Yeah.
Your momentum.
Yeah.
But what is your red and yellowish? You said it's energy?
If I'm correct, yeah, this is like the energy of my reaction to the proton, because I'm just looking at the proton, or 2 protons actually.
Because
you want to say that your probability distribution is offset vertically according to total energy, right?
Yes, exactly.
So it's not energy. I mean, it's a distribution of your of the position of your wave packet, right? It's completely different, observable.
Yeah.
Okay.
We didn't study catalysts that much in this class, but is there any reason you chose platinum instead of another catalyst?
Yeah, other metal catalysts could have been used, but
I thought.
I was just provided with research papers from Dr. Hahn and other people where they used a platinum catalyst, and that's where I got some of my figures my data was from. So
okay.
Yeah.
Okay, let's thank Hannah once again. And next presenter is Beth Badal, who will tell about quantum aspects of the fragmentation of metal organic complexes.
Yeah, so as I said, I'm looking at the fragmentation of metal organic complexes. There we go. Okay, so our fragmentation of any molecule occurs when the molecule gains enough activation energy to surpass the barrier. So this energy can be found in any sorts of methods. It could be thermal activation, photon activation, or the energy from a laser, which is what we're looking at today. So hopefully this video loads. So this is our lanthanide molecule. So as you can see, the bonds are being broken. It's not surpassing the second barrier, so they're being reformed as it goes. And then this is just the general activation diagram. So as it passes the barrier, it gains enough energy to pass the barrier, then it can move into the excited state and then back into the ground state. So lanthanide cyclopentadienide is, so a little background on it, it's highly volatile. And because of this, it can be used to create films for protective coatings at relatively low temperatures. And with that, we can use our laser to excite the LACP into this excited state so that it can form these coatings. So my goal with the MATLAB research was to show this molecule reaching its excited state, passing the barriers, and then at a certain momentum, I should be able to show that it'll pass through both barriers and the bond will be broken. I ran into some problems initially with this. So my data that was given, I had again about 20 points. So we tried to just use this data as was shown, but as you can see, it just kind of tunnels through the first barrier at any momentum. So these momentums are all the same momentums. We're just showing a different starting location. So we tried using starting it in the middle and seeing if it would pass any barrier. Then we tried starting at the end and proceeding backwards, and the same thing happened. It just tunneled through. So to solve that problem, we interpolated more points. We went up to 390 points using the MATLAB code. And then we also reflected the barrier so that we could see both the forward and backward, both the forward and backward views of this. So these videos are going to be showing the momentum going. This one is an initial momentum of 75,000, and then that was 100,000. So as you can see, it is starting to pass through the first barrier here. The one on the right is passing through a little bit more, and it's almost reaching the second barrier. So we did come to more excitable conclusions with this one. We were just able to see the actual process being carried out once we saw both sides. So our conclusions. The bond reached this excited state to pass through the first barrier fairly easily. The second barrier was a bigger challenge. The visualizations show that there was not enough energy to pass through that remaining barrier, so it was converted back into a bond, and it proceeded in the reverse direction.
Okay, let's thank Beth. Any questions? Please.
For your molecule, I didn't get, you break in CC bond or CH bond? Like what
We're breaking up the carbon.
Or you're breaking the bond between metal and carbon?
Yeah.
So yeah, it means
we're
which
breaking
bond is broken?
We're breaking the bond between the metal and the carbon. So
okay.
Like,
so when you say like going through first barrier, it means you broke one bond. Going through the second barrier, you require the second bond is broken. Right?
Yeah, so it's kind of like to get through the second barrier. It still has pull from the central ion. So the carbon is still like in the circle of the attraction between the metal and the carbon. And then to break the second barrier, then it would actually release the carbon. So breaking through the first bond, the carbon is still in the system. And then if you broke the second bond, then it would actually be able to be a free carbon atom.
I see. Thank you.
1, 2, 3. Well, thank you, Beth, once again. So, last but not least, presentation is by Luke Willing, and he will conclude our journey into world of real reactions in giving some comments on possibility of connecting atoms. So, polymerization reaction. What is yours?
All right, everyone. Thank you for the introduction. I did my project on the photopolymerization of cyclohexasilane. Cyclohexasilane is just a 6-membered ring of silane, so Si6H 12. And it's back up. So what's important about this is that it's one of the initial steps in order to create crystalline silicon. Crystalline silicon is important because this is a very important material that we can make into a semiconductor and has applications in photovoltaics and ultimately solar cells. So the main point of my, the main point of what I wanted to figure out is this Si-Si bond on the cyclohexasilane is broken by UV light. So I wanted, the purpose of my research was to figure out how much energy it took to break that and how dependent it was on the initial kinetic energy of the system. And I predict that because this is a surprisingly very little bond difference between polysilane and cyclohexasilane, it's less than like 20 kilojoules per mole difference. I feel like the activation energy is going to, or not the activation energy, the kinetic energy required to excite that electron, break it apart, and start forming the polymer is going to be very small, and it's going to tail off really quickly. So it's going to be a very small window, and initial kinetic energy won't have the greatest effect past that initial state. So to start out, used obviously MATLAB. What I went for with the code-wise, so represents the Hamiltonian operator for a charge transfer potentials. And with mine, my potentials, I use a Morse potential to try and graph the, so you have the well that's, yeah, and it goes to, that basically I wanted to be able to try to show the bond as it's bound and unbound. You'll see once I get to the next slide here. So here's my program that I ran. This kind of tan line is the ground state of the electron within the cyclohexasilane. And then this light green Morse potential doesn't really look like one, but it eventually goes off and does approach the initial zero potential line. And then you'll see here a yellow line that represents the initial state of the wave packet distribution. And the blue line will be the ground state of the electron distribution. And the red line, you can't really see it right now, you'll see it here, it's a video. But you'll see the blue line transition into a red line, and that represents the excited state of the electron. There. So you see the blue line eventually die down, all of it goes into the excited state of the reaction. All right, and so my results. My initial momentum chose for P naught was 23 to 31. This is kind of a small window, so some of my predictions are starting to show through a little bit. Reason I chose these is because it gave me a reaction yield from 9% to 97%. Anything lower or higher than that just kind of started approaching about 95%. It actually, yeah, and then about 5%. So then I plotted the different initial momentums. So the darker the line, the higher the momentum. And this is the probability of the reaction to go through, where 1 being a complete spontaneous reaction and 0, which is down here, being the reaction did not go through. We can obviously see as we increased initial kinetic energy, the reaction had a greater and greater probability of going through completion. And then I took the initial kinetic energy and I plotted it against the rate reaction, which I differentiated from these values. We actually see a nice little curve here. So what we're looking at is as we increase kinetic energy, we see that the rate initially increases for a short amount of time. We're looking on the scale of less than a power, and eventually does start trailing off, and it eventually the slope will approach 0 on that. So it is starting to show results that are very similar to my predictions. So, there we go. So in conclusion, we saw the small window of kinetic energy that the product needed to cause the reaction to go to spontaneity as predicted. We saw how the effect of the initial kinetic energy had an immediate effect on the rate of reaction, initially growing quickly and then trailing off as the kinetic energy continued to increase. And then moving forward with this information, we can use this to begin modeling the rest of the reactions to create eventually crystalline silicon, which can then be used to better understand it, how to create it, because this is a very important material. And thank you.
Okay. Everyone is tired? Yes,
From
please.
the very beginning, I'm a little bit confused. So you have your picture showing how you start with a cyclosilane ring, and then you break the bonds there, and then you kind of creating the crystal from polymers,
Right.
for silicon polymers. So what exactly, which of these processes is connected to this simulation?
Right here. So
the
we
very
have,
first one.
Yep, the cyclohexasilane is being excited by UV light, which, so two of the silicons will break and they both have one electron since it was just a regular covalent bond. And these now to be a radical can now react with the neighboring also breaking up cyclohexasilanes, forming silane polymers now. See here, this is what it breaks up, and then the neighboring
But these processes are not really involved in this simulation anymore, right? Your simulation is stopped there.
Right, yes.
As soon as
It
you
doesn't
broke,
involve
you
the
broke
coming
the bond,
together,
this
it's
is
the
where
breaking
you're-
apart, so it can, the next part is spontaneous, so
Okay.
Assumed to be spontaneous.
Questions 1, questions 2, questions 3. Well, thank you once again. So, concluding remarks. I will be brief because some of you have other things on your schedule. So, many thanks for investing your time into a physical chemistry course. I have about 4 points to mention. First, if you are filling the feedback charts, please return them to me. Second, all participants of these presentations will not regret. The amount of accumulated credit will make you happy, even if something went not perfectly. So you'll be satisfied. Third, in the course, you got 2 or 3 types of major experience and skills. So fundamental knowledge in basics of physical chemistry and quantum theory, exposure to simplified but more or less realistic research style, and scientific communications. This will give you benefits if you entering next course on this track. So if you are entering inorganic chemistry, physical chemistry 2, or computational chemistry, it will make your life in those courses much easier. And if you ever decide to continue in the research pathway, the exposure to research style and scientific communications will help you to excel there. With this, I would like to thank all speakers for presenting and visitors to support the discussion. With this, all meetings of the CHEM364 are done, finished. Class is dismissed.
That is a great feeling. I feel like you should have had that the class over like PowerPoint slide.
I was gonna say, you should
one
have
more time.
last end lecture.
Yeah. That was pretty cool.
Are you going to the Sheeney's?
Yes, it's in 20 minutes.
Okay.
Glad there was not enough question time for parents to ask me the questions.
I'm glad. Did you tell me we had this? Or?
We got Amy sent out an email.
That's all I knew about it.
Yeah, to the whole department.
Oh, geez.
Huh? Yeah.
Yeah. The one you said by, right?
Yeah.
Yeah.
He sent me a picture of that in the morning. Nobody was watching, just like,
Is that all just in class research, or is that one of your like research projects that you just like threw into a class presentation?
Everything is good.
It was all brand new stuff.
Good.
sorry. Can I shoot you an email?
Yes, anytime.
I'm gonna go talk to HR today. To actually get those forms and everything in. Can I just email you and
I will
figure out?
blindly sign in so we can find them.
Okay.
Just
perfect.
few that it is ready for signature.
Yep, besides that though, could you just email me where that desk is gonna be?
I was seeing they were referring to your
Yeah.
potentials.
Can you show Austin the office? Yeah, he's interested to do some research. Okay. And he needs a place to sit. Okay.
Okay, perfect, awesome, thanks. What was your name?
Есть у тебя мусорка? Как его имя? Это тот человек, у которого потенциал забрали. Надо было сразу его представить. Слушай, я что подумала. У тебя, на самом деле, было что-то, ну, я думаю, у тебя получалось что-то похожее, что я хотела тебе сказать. Но можно это сделать немножко более, как сказать, смотри, все равно есть студенты, которые у тебя как бы отказывались. Красивые цветы, только чушь лилий-то нет.
Вот лилии в другом. Я торопился, поэтому взял готовый букет.
Давай этот букет никому не отдадим.
Мы это никому не отдадим, все
А
дома.
этот подарим кому-нибудь. Эми или Дионе, кому там. Кому нам хочется подарить. Так я хотела что сказать-то. Это коробочка? Да. А, ты в ней все можно нести. Классно. Как ты цветы будешь нести?
Все в коробку.
В одном или в две?
В одном. Сейчас запись идет, но я не знаю, как ее остановить. Она...
Записываешь?
Да, она записывает. И непонятно, здесь нет этих кнопочек. Раньше были одни кнопочки, сейчас другие. Recording is in progress. Я боюсь просто, что если я просто отключу, то оно сотрется.
А у тебя supporting team прислал?
Я присылал им, да, так, supporting team, они тоже студенты. Светочка, ты мне дала свою эту, ты писала, кому какие оценки или нет?
Да.
Хорошо. Есть такие, у которых сплошные H.
Ну, вот сразу после С особенно было на контрасте. То есть сначала выступили два очень слабых студента, да?
Я не знаю, по какой причине, но слабые студенты выбрали либо начало, либо конец, а сильные были в середине.
Да, вот сразу после слабых очень круто был два или даже три. Вот розовый мне очень понравился. Он вроде так не очень уверенно отвечал, именно, ну там некоторые просто брали харизмы, ну видно было, что он сразу вышел и уже все, ему уже хочется A поставить. Вот. А был парень вот в розовой рубашке, который здесь вот где-то спереди сидел, я не помню, ну я не помню, про что он там.
Просто на фотографии покажи.
На фотографии так тебе не скажу. На фотографии он без розовой рубашки.
Thank you so much for coming. Yeah. It looks like the recording is still going on, but I fear to push anything to that it will not be recorded.
Yeah, it's still
And-
in progress.
Angela was able to run it for me, but when I'm trying to do it, it asks for system administrator password or something like.
Okay.
Not the way I expected it to function. So the goal is just to keep this recording and upload it in the regular way. If there was a recording.
I think so. Let's see. Create a folder for this.
But until the recording, see these numbers? Is it for connection or for integrity?
No, that looks like a integrity one.
So we are on air. We are recorded now, and it will not stop. It will not process the file until it is formally finished.
I believe so. Let me see what's here. Yeah, there's something up.
it here.
Впечатление, что мандаринов после того, как мы собираемся стол, стало больше людей. Приносить свои, подкладывать.
Did you pause the recording at any point?
I did not.
Okay. Usually I think this time comes up when you pause it.
No, it was on every day.
Oh, it's always there?
Yes.
Okay. And it's still running. It still keeps going up.
I think if I close, I don't want to do it, but if I would close this, it would accept it as a command to stop recording. Maybe it will start uploading.
This is just the site where the recording, like the access to the server.
Mm-hmm.
It's really the software on the PC, and I'm not sure if it's actually. It says it's still running. Let's see. But it's not listed as an active.
Maybe some weapon.
Integrity recorder right there. So it looks like it is still running, but without the taskbar.
And I noticed it in other classroom as well. In the EML, taskbar stopped to pop up.
How weird.
And then it asks whether I want to download and reinstall Integrity recording.
Okay.
And then it doesn't accept my password and tells that it should be a system login.
Yeah, if you go directly to the integrity site here, it will want a password, like an integrity specific password.
Mm-hmm.
Where the way you send in, you go to Blackboard, and then you authenticate through Blackboard. And that should work usually. But what I'm doing right now, here for example, this is the integrity specific password.
Okay.
I'm trying to figure out how to stop it. But it's really odd.
Did you make 2 recordings at the same time?
I think the recording is running normally and everything is fine, other than that the taskbar malfunctioned and disappeared. And so I'm just trying to figure out how to stop this recording without losing it. Because if it would just restart the computer, it would stop the recording. But at that point, I don't know if it would actually then finish it and upload it, or if it would somehow corrupt it.
Erase everything and consider
Yeah.
this empty file.
I'll play with this.
Well, thank you so much.
Yeah. I'll try to figure out what's going on. Oh, thank you.
Well, I hope a lot. I trust that you will succeed.
Yeah, I'll work on it. I'll make sure to get it done somehow.
Okay. Many thanks for continuous help.
Oh, absolutely. You're welcome.
Bye-bye.
Bye. Hey, I got a question for you. Do you have a minute? And maybe it's for Trevor too. I don't know if either one of you guys have run into this. So there's integrity recording running up here in 422. And it appears that it's still running. Everything seems fine except that the little tray that you usually have in the taskbar is gone. So there's no way for me to stop the recording. So I'm trying to figure out how to stop this. I don't want to just force this application to close or restart or something because I'm worried that I'm going to lose the recording.
Right.
Have you seen it? I've heard of this before, but I've never actively been in the room trying to stop it. I've heard that it disappeared and then people would usually just restart, but I can't remember if they then lost it or if it somehow was still saved.
Yeah, Trevor, have you heard of the integrity taskbar just going away? What the result was then? Yeah, Trevor never had to go away on him either.
Okay.
I wonder if it's on like a different screen or something and it's like trying to be duplicated somewhere. And I don't know. Yeah, I'm just standing in the dark here, so.
I can change the display settings and go back and forth a little bit. Maybe they'll do something. Okay, let's see.
Well, Trevor and I can run up there and help you troubleshoot it a little bit.
It's up to you.